each other, reflecting and scattering the light to produce a variety of colors. This microstructure is also often seen in bird feathers. What all of these examples have in common are periodic microstructures spaced at intervals of about 380 to 780 nanometers, which is the visible light spectrum. As long as the microstructures stay physically intact, structural colors will not fade over the passage of time.
こういう自然界の非常に鮮やかな色を人工的に再現したいんです。
Kori completed his graduate studies at Tohoku University in 2007. He then worked as a researcher at France's Claude Bernard University Lyon 1 before becoming an associate professor at Chiba University in 2015. Kori has long been conducting research using a polymer called polydopamine.
これがポリドーパミンの溶液です。この材料を使って接着剤などの開発を行っていました。
This black dispersion of polydopamine is what led Kori to the world of structural colors and played a leading role in his later research. Initially, Kori's research had nothing to do with structural colors, but one day, something happened that drastically changed the direction of his work. This was in 2013. A student conducting an experiment on polydopamine told Kori that she'd created something strange. The polydopamine, which was supposed to be black, had turned into a shiny green substance. Initially, he thought that some kind of chemical reaction might have created a pigment, but he soon found that was not the case.
あのような緑色がなぜ出るかというのは全く分からなかったんです。でさらにあの材料は時間が経つとまた元の黒い色に戻ってしまうということで、それがより私たちを悩ませました。
How did a black liquid turn into a metallic green substance? Kori set out to solve the mystery using various methods. He discovered the secret in the surface structure. The arrangement of the polydopamine particles created a microstructure, which is one of the typical patterns that produce structural color. Here is an electron micrograph of the surface. The particles appear to be lined up neatly. Kori thought that by applying this technology, he could develop completely new inks and paints based on structural colors. In order to achieve this, Kori stopped conducting research on adhesives and shifted to a new research field.
私の知っている中では非常にはっきりした色の構造色で、この色をインクとして再現することができれば、構造色の色あせないという特徴を生かした新しいインク状の材料ができるというふうに感じました。
In the course of his new research, Kori learned that the mechanism of the structural color he had created by chance resembled that of a certain creature. That creature was a peacock. The microstructure in bright peacock feathers was very similar.
クジャクの羽の中では、ロット状のメラニン顆粒と呼ばれているものが基側構造を形成していて、その微細構造由来の色がこのクジャクの構造色であるということを知りました。
This is an electron micrograph of a cross-section of a peacock feather. We can see that it has a periodic microstructure formed by granules. The microstructure of these granules causes light reflection and interference, producing the structural color. The microstructure of the granules resembled the polydopamine microstructure that had been created by chance. Moreover, something else about the microstructure of peacock feathers was key. The granules are melanin. Melanin is a black pigment found in both humans and animals. Black hair color is due to melanin. It's also found in squid ink. In fact, melanin also plays a different role in creating structural color and making it more vivid. Normally, a microstructure will reflect light of a certain wavelength and at the same time cause other light to scatter. However, black melanin granules absorb the scattered light, so only the reflected light is clearly visible. The vivid structural color of a peacock feather is produced by the melanin granules. Coincidentally, the polydopamine that Kori and his colleague used in their experiments was similar in composition to natural melanin. Looking at the chemical structure of both, we find that they are very similar. Essentially, polydopamine has the characteristics of artificial melanin. The structural color that had appeared by chance was because the polydopamine was behaving like melanin. Kori tried to make use of this accidental product, repeating experiments to develop an ink using polydopamine particles. Eventually, he succeeded in creating a dispersion of polydopamine particles that could be used to produce structural color. Here is the dispersion. After releasing a drop and letting it sit for a while, water in the fluid evaporates and the color changes to a deep green with metallic tones. This is the mechanism of coloration. As the water evaporates, the loose particles of polydopamine form an array structure. This microstructure produces a green structural color from incident light. Once the water is completely gone, the color will not disappear over the passage of time, a big step toward perfecting structural color ink. Kori's paper summarizing the results was cited in many publications. This was the first time structural color was successfully created with polydopamine particles that mimic melanin. Kori continued his research on the practical use of structural color inks. However, there was a problem with this dispersion.
インクとして使うと乾燥させた後に非常に綺麗な構造色は出たんですけども、粒子の色が黒すぎるために全体的に構造色が暗くなってしまったんです。
Here is a pellet made with structural color ink. Compared to the green in a peacock feather, indeed we can see that the color is not as bright. While searching for an alternative, Kori heard about the feathers of another type of bird from a biologist who was also involved in biomimetics research. That bird was a turkey. Turkey feathers also have structural colors. Though not as flashy as the peacock's, the colors in these feathers are also created by melanin granules. In fact, there is something about those granules that is unique to turkeys.
七面鳥の羽の中ではクジャクの羽とは異なり中空構造のメラニン粒子が使われているということです。例えばこちらのテニスボールのように中が空洞になったようなメラニン粒子になります。
This is a schematic diagram of a melanin granule in a turkey feather. The granule looks like it's made of a melanin shell because it's hollow. Cody thought if a similar structure could be reproduced, the thin layer of melanin would prevent the black color from appearing darker, allowing for brighter colors.
例えばナッツの表面にチョコレートをコーティングするとします。この際にコーティングするチョコレートの厚みを変えれば黒の割合を変えられるというイメージです。
Cody then decided to create a type of particle called a core shell. Surrounding the core particle by a thin coating of polydopamine, which is similar to melanin, should result in a structure similar to the melanin granules in turkey feathers. He reasoned that if he could change the thickness of the polydopamine, he would be able to adjust the brightness. For the core particles, Cody decided to use polystyrene particles, something he often used in his research and which are also used in styrofoam. He thought they would be easier to coat with polydopamine because he knew the characteristics of their surface structure well. Sure enough, polydopamine, the artificial melanin, successfully coated the polystyrene particles, producing the core shell type particles he expected. This is the new ink created with those core shell particles. It appears quite different from the first ink with the polydopamine particles. Let's see what happens with a drop of this ink. As the ink dries, the core shell particles become neatly arranged, producing bright and vivid structural colors. Moreover, the structural color can be controlled by changing the core particle size. Watch what happens when writing with a structural color ink that produces blue. There are still some improvements to be made in terms of viscosity and drying performance, but the metallic hues unique to a structural color are clear. Here is an illustration drawn with 3 structural color inks. None of them contain any pigment. In addition, the thickness of the polydopamine can now be adjusted. By controlling the size of the core particles and the thickness of the surrounding polydopamine, Cody has been able to create all kinds of structural colors. After repeated experimentation to adjust hue, saturation, and brightness, Cody and his team are now able to create almost all artificially produced colors. Cody is now tackling the last major challenge for the practical use of structural color ink. That challenge is how to maintain the structure over a long time. These are pellets made with the current structural color ink. Grind up the pellets with a mortar and pestle. and the particle structure breaks down, resulting in a brown powder.
微細構造を維持するためには粒子配列を固定する必要があります。粒子同士をつないでおかないと構造が乱れてしまうからです。この微細構造の維持のためにはいろいろな添加物を加えることになりますけれども、この添加物は粒子配列を維持するためにも重要ですけども、添加物を加えすぎると逆に配列構造が乱れてしまいます。このバランスを取るのが非常に重要で、今新しい方法も含めていろいろな手法を模索しています。いろいろな人と協力しながら5年後10年後ぐらいをめどに